deriving general relativity, I mean, by means of the equivalence principle. And I just put it into these pictures, and we have here Kibble slab. And here, so this is, I think probably I need more than one blackboard. Okay, so what is the elementary object in special relativity? Elementary object in special relativity. The elementary object in special relativity is in Einstein's laboratory a mass point, m, with velocity v. Or I could call it four-dimensionally immediately ui for velocity. In Kibble's laboratory, we have a Dirac spinor. Psi of x of mass m, and it has 4 different components, as you know. Components, 4 components. Okay. Then, so these are the elementary objects and the study. So this is typically a cow experiment that's typically a mass point related form. And then you have an inertial frame. In Einstein's case, it's a Cartesian coordinate system. Cartesian coordinate system with coordinates xi. And in the inertial system, that is in this coordinate system, ds square, is in this coordinate system star equal, the star is in this special system, is Oj dxi tensor dxj. Oj is a Minkowski diagonal matrix. Now, for a Dirac spinor, we need a frame, but in special relativity, it's sufficient a holonomic orthonormal frame. Holonomic orthonormal frame. Orthonormal frame. So this is E alpha, frame. And since it's holonomic, it's a natural frame. So in this, under this special circumstances, it's delta I alpha. Delta is the Kronecker symbol partial I. And we have that. Well, I can put it E alpha dot E beta, if that's a scalar Buddha, is equal to alpha. Now the force-free motion, that is, I don't apply any force to my particle or my object. So that's a force-free motion in inertial frame. Inertial frame I call IF. Force-free motion in IF. Of course we know if there is no force, the acceleration of this particle, ui dot, where the dot refers to the proper time, is equal to 0 in this frame. And of course, the Dirac equation, I gamma I partial I minus m applied to psi is equal in this frame to 0. So the force-free motion is just acceleration is 0, but in the Kibble slab, it's the Dirac equation in this orthonormal holonomic frame. Now we go over to a non-inertial frame. Non-inertial frame. Non-inertial frame. I call NIF. In non-inertial frame, you know, it's described by curvilinear coordinate system, by a curvilinear coordinate system. And in a non-inertial is no longer holonomic, but an n-holonomic orthonormal frame. Orthonormal frame. And we write it down. And the coordinates, the curvilinear coordinates, we can x dash I, and the n-holonomic, I have a frame, which is E alpha equals EI alpha. These are the Quadratic coefficients times partial I. Or I have a co-frame, which I denote by theta alpha equal EI alpha dx. So these are non-inertial frames. Okay, and now I have to describe my force-free motion in non-inertial frame. Force-free motion in non-inertial frame. And here I see in an inertial frame I get just vanishing acceleration, but of course in a non-inertial frame I know that I get ui dot, but then I pick up two terms plus u say k ul times the Christoffel, which I denote by gamma Drittel KL and upper index I, and that is equal to 0. And in the Dirac equation, I have to generalize this now to an n-holonomic frame, and how this is done, you have I, gammas refer now to the orthonormal frame, gamma alpha, they are constants, but then I have to insert here the EI alpha, the components of the frame, parenthesis partial I plus, and here is the gamma I, this is the connection, the Lorentz connection applied to psi. No, minus m. Minus m applied to psi is equal to 0. So here I picked up this Christoffel symbol. This is a result of this is a result of this non-inertial frame. I'm still in flat space-time. There is no gravity, nothing. And here I pick up now this potential, which are really 16 independent components, and this. This is the Lorentz connection, which I should write out in order to make it clearer how this is defined. The Lorentz connection, gamma I, is here defined. It's if I take the usual conventions, I over 4 times gamma, the connection, I alpha beta times F alpha beta, where alpha beta for the Lorentz, for the spinor, are just the sigma matrices. So I can better take here the sigma matrices for the Lorentz connection. So you see that I get here one new element, and here I get two new elements, and I should really make this red around this in order to see how many components you have here. So this is to be, this red is to be erased. I think it's clear if I do it this way. So you can see that I get here, this is anti-symmetric because the sigma matrices are anti-symmetric. So these are 6 times 4, so these are 40 components. And this is 4 times 4, these are 16 components. And this Christoffel symbol, which can be derived from the metric, but as Christoffel symbol, it has it's symmetric in K and L, as you can see here. So this is 10 times 4, this has also 40 components. But it can be derived from the metric by differentiation, and the metric has 10 independent components. So in the non-inertial motion, we see that we pick up new terms. Incidentally, this with the Dirac equation, I investigated together with Professor Ni very carefully the paper. I mean, that was at this time when I was, I think, the second time in Taiwan. I'm 89, and we wrote a paper where you can find the details if you are interested. It's a very short paper. It's Hehl and Ni. It's Visual Review B, number 42, 2045, and it's published 1990. What we do is we take the Dirac equation, formulate very carefully all these quantities, and then make a WKB approximation, and then in order to recover the non-relativistic approximation, and then we get such a term like in the Cow experiment. So this shows that this is consistent with each other. Okay, so now we are in a flat space-time, so still we have certain constraints in special relativity. We are still in special relativity. All we did is to investigate non-inertial frames.
So this process would be before alpha beta is anti-symmetric.
What?
What does the answer gamma I?
This is 6 times 4. Oh.
But add together for the
No, you are right. 6 times 4 is of course 24, and these two together is 40. Right? Sorry. This is anti-symmetric, so anti-symmetric is 6 times 4. These are 4, and this is 24. So it was not was an error. Okay. Well, I mean, so the new object which occur are these with 40 and these to 16 plus 24. But we have constraints, namely that the curvature tensor and the Riemannian curvature tensor is a little, depending on the partial derivative of this Christoffel and the Christoffel itself, that this has to be 0. Curvature is equal to 0. And this corresponds to 20 conditions. 20 conditions. And here, of course, this is now a new independent quantity, and you have to have the constraints for both of them. As you learn in geometry, for instance, the constraints are that the torsion, which depends on the first derivative of the ease, and on the ease itself, and on the gamma, is equal to 0. These are 24 conditions. And the curvature, which is no longer a Riemann curvature in general, but the curvature, depending on gamma, d gamma, and gamma, is also equal to 0. And this corresponds to 36 conditions. So you can always... So these constraints, and it's very important. So if you have such a constraint, which means that just the space is a Minkowski space. Here you have torsion equal to 0, curvature equal to 0. Here you have the Riemannian curvature equal to 0. Since if you have two such objects, you can build two quantities, two tensors out of it, and these are just the torsion and the curvature tensor. But still, in a global inertial frame, you can always, since you are in special relativity, in a global inertial frame, you can always introduce that the Gij is globally the Minkowski. And then, of course, the Christoffel symbol vanishes. The Christoffel symbol vanishes. Here it's a bit different. If you have the co-frame, E alpha I, whether you take the frame or the co-frame, basically is free choice. But usually one takes a co-frame because this has the property of a potential, and this frame has not a property of a potential. So for that reason, one takes usually the co-frame. So the co-frame and the gamma can be in such a global frame, alpha beta, normalized such that the frame becomes a Kronecker, I alpha, and the connection vanishes. So also in these anholonomic frames, you have more degrees of freedom, and you can not only transform the coordinates, but also the frames. And so it's always possible to bring this gamma locally at one point, globally everywhere to 0. And this just is then a natural co-frame, as you can see. Okay, now this is the preparation of Einstein and of Kibble, how to derive the gravitational theory. So what has happened? By studying objects and by carefully distinguishing inertial and non-inertial frames, we were able to identify the gravitational field which is appropriate to the object you consider. Here it's a Christoffel symbol. If you consider the Dirac spinor, we have two quantities which is turns out to be related to translational gauge invariance and this to Lorentz gauge invariance. So without switching on the gravitational field, just by going to a non-inertial frame of reference, we have this information. So Okay, now I usually here I have the archetypal experiment. You know, this is just for Apple in gravitational field. Apple in gravitational field. This is Newton, of course. And here you have a neutron in gravitational, the neutron in gravitational field. But not only a neutron, but a neutron wave. So so the cow type experiment. So this is when Newton thinks about his gravitational field, he thinks of the apple, presumably falling on his head, but we can only think of the cow experiment in this situation, and this makes the difference. I mean, there was a book on relativity by Tsing, where he discusses these analogies between apple and neutron. He says that the behavior of a neutron in the gravitational field is not like that of an apple. He has also a nice saying in this. Okay, and now switch on gravity. Of course, this is also switch on. I mean, it's always there. If one makes special relativity and neglects gravity, it's only in a certain approximation possible. So switch on gravity is only sort of switch on gravity. And then, of course, Einstein just said, well, let us forget this constraint. So the curve for the Christoffel symbol unequal to 0, and this gives a Riemann space. Riemann space. Okay, now Kibble switches on his gravitational field, and he gets torsion is unequal to 0, and curvature is unequal to 0, and this yields a Riemann-Cartan space, which we already studied to some extent. Okay, and but still, and this is also, this is often misunderstood. For that reason, I put it here again. Locally, at one point and its surrounding, locally, at one point, we can always introduce in a Riemannian space Riemannian normal coordinates, and then the Gij at this point P is just the conic, the Minkowski, Oj, and the Christoffel at this point, Ijk, at this point is equal to 0. So this is what is popularly called the Einstein elevator. In an Einstein elevator, you are in free fall. At this point, you only feel the Minkowski space. The gravitational field is at this point transformed to 0. And we have a corresponding elevator, but this is now a bit more refined because we have now also aeronomic frames to take care of. You get EA alpha, which is the coframe, and the gamma, I alpha beta, at one point. These two quantities at one point are equal to Kronecker and 0. So often it is said this cannot be true because torsion is a tensor and you cannot get rid of a tensor at one point. Well, the same is true for curvature. Curvature is a tensor and you cannot get rid of the curvature at one point. However, if you look for a point in its neighborhood where only the homogeneous part of a curvature is relevant, then you can really transform it to zero.